Hey guys, today we are going to learn about the degree of static and kinematic indeterminacy concepts. Let's start with the first question. Degree of external static indeterminacy of a propped cantilever beam subjected to general loading is. So here you can refer the diagram of a propped cantilever beam subjected to general loading type. So what is the degree of static indeterminacy here in this structure? Here the correct option is option A. Degree of static indeterminacy of this propped cantilever beam having general loading is 2. So let's see what is the formula and how to calculate that. So degree of external static indeterminacy is given by DSC is equal to RE minus R. So RE is the external reactions and R is the equilibrium equations that we have. So here you can see one vertical reaction is here and one horizontal reaction and one moment will be there. And in this support we have one vertical reaction, we have one horizontal reaction. So in total we have 5 external reactions and we have 3 equilibrium equations, nothing but moment summation of moments is equal to 0, summation of fx is equal to 0, summation of fy is equal to 0. That is moment, vertical reaction and horizontal reaction. So we have 3 equilibrium equations and we have 5 external reactions. So 5 minus 3 is 2. And let's see some points regarding statically determinate and indeterminate structures. So when a structure is statically determinate, that is ds is 0, then shear force and bending moment are independent of that material and independent of cross-sectional area. That is nothing but SF and BM will be dependent only on the type of loading which is provided on that structure. There is nothing to do with the material or the cross-sectional area, or simply we can say axial rigidity of that beam or structure when that structure is statically determinate. There will be no stresses due to temperature changes. In case of the temperature changes, there will be no stress concentration in anywhere in case of statically determinate structures. In case of statically indeterminate, there will be stresses and no stresses due to lack of fit and support settlement also. So this will be applicable in case of statically determinate structures, and in case of statically indeterminate structure, exactly opposite of its kind. SF and BM will be dependent on material and cross-sectional area in case of indeterminate structures, and stresses due to temperature changes, lack of fit, support settlement will be existing in case of statically indeterminate structures. And those statically indeterminate structures are also called as hyperstatic structures. And to calculate the reactions and to resolve the statically indeterminate structures, we require an equation called compatibility equation, apart from equilibrium equations that we already have. So compatibility equation means it will be with respect to the deflection slope. So using deflection criteria, we have to provide the compatibility equation so that we can find the reactions and solve the given beam or structure. So compatibility equation will be required in case we have to solve the statically indeterminate structures. Now let's move on to the next question. Degree of total static indeterminacy of the plane shown is. So we have to find the total static indeterminacy of the given structure. So here total means we have to calculate the summation of internal static indeterminacy and external static indeterminacy. In the previous question, we have calculated the external static indeterminacy of a beam. But in beam, we have only external static indeterminacy, and internally a beam is always determinate, statically determinate. And here we have to calculate total static indeterminacy, like summation of internal plus external static indeterminacy of this structure. Here the answer we have got is option C 8. Let's see the calculation and formula. Degree of internal static indeterminacy of rigid frames is given by dsi is equal to 3c minus r suffix r in case of two-dimensional rigid frames, and in case of three-dimensional space frames we have dsi is equal to 6c minus r suffix r. And here in this diagram we have two-dimensional. And what is the degree of external static indeterminacy? As we have already seen in the first question, that is r suffix e minus equilibrium reactions. And here similarly we can find, so here you can see we have one vertical reaction, we have one horizontal reaction, we have one moment. So in this support we have three external reactions and in the same way in this also 3, in this also 3, and this also 3. So how many total external reactions we have? 12. And we have three equilibrium equilibrium equations. So 12 minus 3 is 9. That is nothing but DSE, that is external static indeterminacy of this rigid frame. And let's calculate the internal static indeterminacy. 3C minus R suffix R. What is C here? C is the number of closed loops. We have a closed loop here, we have one closed loop here. So we have two closed loops in this given structure. That is, here one closed loop, here one closed loop. And let's calculate the force releasers. So we have one force releasers, vertical shear releaser here, and we have another force releaser here. And but in this force releaser, there are two components are released. One is moment is released since it is a hinged support, and one is horizontal movement since it is a roller support. So we have released two things, one is moment and one is horizontal in this support. And in this releaser we have released this shear, vertical shear. So here also one releaser, here also one releaser, and again we have one releaser, one force releaser here, that is horizontal roller. So internal horizontal roller that is releasing horizontal movement. So here one releasing, and we have internal hinge here. So this hinge is connected by four members. So when a hinge is connected by m dash members, then we have to release m dash minus 1 releases. So here four members are connected, so 4 minus 1. So by this internal hinge we have released three forces, 4 minus 1 3. So totally we have force releases as 1 plus here we have 2 and horizontally 1, and because of hinge we have 3. So we have to minus. So 3 into 2 6 minus of, so we have 3 4 and 7. So DSI is equal to minus 1, and we have already external static indeterminacy as 9. So total static indeterminacy is 8. 9 minus 1 8. So in this problem we have calculated how to find the internal static indeterminacy and external static indeterminacy of frames, rigid frames. Now how to calculate the force releasers. So in this diagram we have vertical shear releaser, roller, horizontal roller, hinge, internal hinge. When it comes to internal hinge we have to use this formula m dash minus 1. How many members are connected to that internal hinge? Here we have 4 members connected to that internal hinge, so 4 minus 1 3. So 3 force releases due to this internal hinge. So accordingly we have to calculate the force releases. We have this frame as two dimensional, so that's why DSI is equal to 3C minus R suffix R. Or we can use this formula also in case we don't remember, or use this. DS is equal to 3M plus RE minus 3J minus RR. So M is the number of members, RE is the external reactions, J is the number of joints, RR is the number of force releases. So this equation is given for two-dimensional plane, and this equation is given for three-dimensional plane. We can simply use this formula when we know how many number of closed loops are there in the given structure. Now let's move on to third question. Given structure is statically, we have to find whether it is determinate or indeterminate, and internally whether it is stable or unstable. So given structure is a truss like structure, we have to find the static indeterminacy. When it comes to 0, then that will be called as determinate structure. When it comes to greater than 0, then that will be called as indeterminate. And here we can see, if we calculate the degree of static indeterminacy, ds will become 0. So that's why this structure is determinate. And in case of stability of this structure, here we can see the component U4, L4, L3, U3. So this component is unstable. It can sway in horizontal direction. So that's why this structure is internally unstable. So we have to design the structure in an unstable manner. Now let's see the formula for static indeterminacy of truss. So degree of internal static indeterminacy of truss is given by DSI is equal to m minus of 2j minus 3. So here we have how many members? So let's calculate that. 1 2 3 4. So in this 4 members, so similarly we have 5 6 7 8 9 10 11 12 13. So totally 13 members we have, and j is the number of joints. We have 8 joints here, and 3 is the equilibrium equations. So upon the calculating or substituting the values, we get dsi is equal to 0. So that means internal static indeterminacy is 0. That means stress is statically determinate. And similarly we can calculate the dse, that is external static indeterminacy. So you can see here we have one reaction here, and we have one reaction here, because these three are roller supports. We don't have moment, and we don't have horizontal or other side reaction. So we have three equilibrium equations. So 3 minus 3 is 0. Again, external static indeterminacy of this given truss is 0. So both internal and external static indeterminacy of this truss becomes 0. That's why the given structure is statically determinate. And when it comes to stability criteria, this structure is internally unstable, because you can see in this frame there is no diagonal member. So that's why it is internally unstable. But here you can see there is one extra diagonal member. So that means it is over stiff. This member is over stiff, and this member is unstable. So that's why as a whole this structure is unstable. And when dsi is equal to 0, that is when dsi, that is internal static indeterminacy of the truss, is 0, then that truss will be called as perfect truss. When it is greater than 0, then that will be called as internally indeterminate and overstiff. When it is less than 0, it will be internally deficient and geometrically unstable. So these are the inference that we have to note from the degree of static indeterminacy. Now let's move on to kinematic indeterminacy. Degree of kinematic indeterminacy of an axially rigid beam pin jointed at both ends. So you can see or refer the diagram for the axially rigid beam having both the ends pin jointed. There is no roller support, both the ends are pin jointed. Then how to calculate the degree of kinematic indeterminacy? We have already learnt about degree of static indeterminacy. Now in this question, kinematic indeterminacy. Let's see the formula. So this k is equal to 3j minus re minus m double dash plus r suffix r. So j is the number of joints, re is the external reactions, m double dash is the number of axially rigid member. Number of axially rigid members that is in the structure, and r suffix r is the force releasers. So here you can, there is no force releasers in this rigid beam, so r suffix r is 0 here. And how many joints are there? Two joints, here one, and both the ends we have joints. So 3 into 2 6 minus how many external reactions we have? Here one vertical reaction, here one horizontal reaction. Similarly we have here also. So 4 external reactions we have. So 3 into here 2 joints, 4 external reactions, no force releasers. So what happens? 3 into 2 6 minus 4 is 2. So what about this m double dash? So m double dash is the number of axially rigid members. So they have mentioned axially rigid beam. That means this beam is axially rigid. But we don't have to consider m double dash as 1. Why? Because the horizontal movement is already restrained by the supports. So that means whether the beam is axially rigid or axially flexible, horizontal movement is already restrained. So that means m double dash equal to 1 we don't have to consider here in this case. We have to be careful when we have to consider m double dash, and when we don't have to consider m double dash. That is number of axially rigid members that we have to subtract in that degree of kinematic indeterminacy. So what happens is, what literally is the degree of kinematic indeterminacy? That is nothing but degree of freedom. So here we have one rotation freedom here, and in the same way one rotation freedom in the other support. So that means two freedoms are existing in this beam structure. Or simply we can use this formula to find the degree of kinematic indeterminacy. So this is in case of two-dimensional thing, and in case of three-dimensional, we have to use this relation 6j minus r e minus m double dash plus r suffix r. R suffix r is the force releasers, m double dash is the number of axially rigid members. But we have to be careful when we have to consider this m double dash. And r suffix r is given by m dash minus 1. M dash is the number of hybrid joints. What is meaning by hybrid joints? That we have already seen in the previous one of the previous questions, that is internal hinge, vertical shear releasers, internal horizontal releasers. So those joints are called as hybrid joints. So when we have hybrid joints connected with some members, like for example one hinge is connected with 4 members, then 4 minus 1 is 3, so that is the r suffix r value that we have already seen in one of the previous questions: hinge, vertical shear releaser, horizontal releaser. Now let's move on to next kinematic indeterminacy question. Degree of kinematic indeterminacy of the axially inextensible frame shown is. So we have been given the diagram for the rigid frame, which is having members axially inextensible. So that means all the members are rigid. We have to calculate the degrees of freedom, that is nothing but degree of kinematic indeterminacy of this frame. So here the answer is option A, 14. So let's see how to calculate that. We can calculate simply using this formula, or we can use the concept of degree of freedom. So here in the support you can see 1 degree of rotation is here, and in this rigid joint we have 3 degrees of freedom. Similarly we have here 3 degrees of freedom, again here 3, again here in this rigid joint we have 3 degrees of freedom. So upon adding all the things, so we have 4, 7, 10, 13. So 13 degrees of freedom we have, and we have also the internal hinges. We have 2 internal hinges. So in case of internal hinge, degrees of freedom will be 4. So we have 4 degrees of freedom in this internal hinge, and in case of internal hinge connected with 4 members, then how many degrees of freedom will be there? In case in an internal hinge 3 members are meeting, then dk will be 5. In this case we have 4 members connected to that internal hinge, then degree of kinematic indeterminacy will be 6. So totally we have 23 degree of kinematic indeterminacy in this rigid frame, and they have mentioned clearly that axially inextensible. So that means we have to reduce the number of rigid members. So how many members are there? We have totally 9 members. So upon just counting all the members, we have totally 9 members. So that's why we have to subtract the number of members, because they are all of axially inextensible. So that's why 23 minus 9 is 14. So degree of kinematic indeterminacy in this frame is 14. So either we can use this formula, or we can use the concept of degrees of freedom using force releasers and at support what is the degree of freedom is given. So that's all about this video. Please like and subscribe the channel. Thank you for watching.